Reese.
Hi, folks. It's great to be here on a beautiful, hot, sunny morning in Petaluma. Yes. Before we begin, I need to give a bit of a content warning. I don't know how to say this, but I'm going to show code. Lots of code. And I'm going to move quick. Most of the code will be small snippets with large fonts, so it should be easy to read and follow. But don't worry about trying to catch it all on your phone. I'll share a URL at the end that has everything, including the code, the slides, my script, everything. So, I was planning to give you all an ultimatum to go with this talk title when I wrote all this last year. I think we've had enough threats in the world lately. It's kind of hard to imagine punishment worse than what we're already going through. So instead, let's just try to have fun with this and ignore everything else. So let's start with defining terms. What do we mean by control flow? Well, this refers to any part of our code that tells the Python runtime how to alter the flow of execution from one line of code to the next. Hopefully, you're already familiar with the fundamental building blocks of control flow. That's conditionals, loops, functions. Every other form of control flow can be expressed as a combination of one or more of these three basic mechanisms. And of course, Python has many different types of control flow, all of which are defined as part of the language grammar. We can even look at Python's grammar specification and see all of the possibilities. You caught all that, right? Obviously, that's a lot. And thankfully for you, I'm not here today to teach you about language grammar. And I also assume everybody here is familiar with the basics. So instead, let's look at some ways we can use the less obvious parts of the language and tools that Python gives us to manage control flow in our projects. Comprehensions are relatively unique to Python among mainstream languages. At their core, comprehensions are really just syntactic sugar around for loops and if blocks, the primary purpose of building collections of data. Now, ignoring performance, these two pieces of code produce identical results, but the key difference is in readability. Now, slightly ironically, opinions of which is more readable will vary depending on familiarity with Python or other languages. As we make the comprehension more complicated, we should consider the benefits and trade-offs of performance and compactness against readability and maintainability of the code in question. I don't think many would argue against using a comprehension for a simple operation like this, but what about now? Here, we're adding a second for loop to the comprehension, but because of the way that comprehensions work, we're forced to order the clauses out of contextual order, obfuscating the intention of the code. So manual reformatting can help. I do think this improves the readability, but at this point, it's becoming harder to argue which of these two methods is actually easier to read and understand. So where do we draw the line? One thing to consider is that multi-line comprehensions like this hide away the inherent cyclomatic complexity of the code. It's a single comprehension, of course, so it must be fast. Whereas the traditional form of this code, it requires multiple levels of nesting, making it much more obvious to the reader that this will likely result in slow performance on large data sets. And really, our choices as developers impact code readability, and thereby impact the maintainability and reliability of our software. We must weigh the advantages and disadvantages of our approaches and consider not just the performance of the code, but our confidence that future changes won't cause bugs, or even just the cost and time and experience needed to understand and modify our code after it's already been shipped to production. We need to consider what the right choices and trade-offs are when writing our code. So, with that said, let's look at some of the less obvious parts of the language and see if we can't find ways to improve the readability of our code in the process. In particular, let's look at the else block, mostly known for its use with an if statement, but it can be paired with other code blocks as well, like in exception handling, where we can use the else block for some common code patterns. As many of you are likely aware, adding a finally block to try except gives us a way to run some code afterwards, regardless of whether an exception is raised or not. By comparison, the else block is only run if there was no exception raised. You can think of this like setting a success variable and then checking that value later, either in a finally block or outside of the try except entirely. I'm sure many of us have seen code patterns like this in the past. Maybe that code should have just been an else block. Python gives us that logic for free, and it's fewer lines of code in the process, less to comprehend. This lets us maintain the best practice of minimizing the amount of code inside the try block itself, while also minimizing effort needed to track whether our code was successful. But beware, unlike finally, return statement here will not execute the else block. So either keep the return statement outside of the try block, or be sure that critical code remains in the finally block instead. Now we can also use the else block in loops, somewhat analogous to its use with try except. Here, the else block is executed if and only if the for loop exhausts its iterable. But if the for loop reaches a break statement, then the else block is skipped. So you can think of this like try except, but instead of executing if no exceptions are raised, it executes if no breaks are raised. We can imagine this code pattern. We're iterating over some data and break on the first time we find a match. Now, instead of maintaining new variables to handle cases with no match, we can replace that logic with an else block, simplifying our code and hopefully making it more readable in the process. Our last use case is for the while loop. Like for loops, the else block here executes if no break was reached, but we can also think of it in a better way. The else block runs when the condition of the loop evaluates as false. Functionally, it's equivalent to an infinite while loop, where you nest an if-else block inside and break out of that loop once the condition's false. But again, once a break statement is reached, the loop condition won't be reevaluated, and that else block will not be evaluated. So, now we're going to jump down the rabbit hole. Let's look at the ways we can use or abuse some of the tools that Python gives us, things that we might not think of as control flow. Like decorators, fun little things we can tack onto our functions and methods and classes. Some of the best inventions in Python have come out of decorators, like data classes. But really, decorators are just callable objects, using syntactic sugar from the language. If you add the @decorator above our function, it's shorthand for calling that decorator, passing it our function, and then overriding the function with whatever the decorator returns. Making a decorator is as simple as writing a function, only this one takes another function or class as an argument, does something with it, and returns a new object when finished. The most common decorators are simply function wrappers. They define an inner function wrapping the original one, do something interesting, and then call the original and return the results up the stack. This might be something as simple as logging every time a function is called. Our greet function can then add the log calls decorator, and every time we call it, we now automatically get logging output that includes the name of the function and the arguments it was called with. But what makes a decorator control flow is key. Using this @decorator syntax is literally calling and executing the decorator's code at the moment that the function or class it's wrapping is defined. This means our decorator will execute before the function or class is ever used, and if we import this code, we'll see that before we ever even call it, the decorator's already printed its message, at import time no less. When we do this call, the outer function, the decorator runs again to process the inner function, even though it's never called or used. But decorators don't have to return functions, or methods, or classes, or callable. They don't even need to return anything at all. All that matters is using the syntax implicitly calls your decorator function. Now, quick side note. One of the first programming languages I learned as a kid was Perl. It has a few variants of loops that invert the expected conditions of the loop expression. The until loop is the inverse of the while loop, and it will repeat the body of the loop until the expression evaluates as true, rather than looping until it's false. I think that's kind of neat. So I replicated the until loop in Python using a decorator. In its most simple form, it takes a callable as the loop predicate and calls the wrapped function repeatedly until the predicate evaluates as true. But this decorator doesn't return a new function. It simply starts running immediately on definition. So now we can write, until loops. But in Python, the loop body will be called until the predicate, the lambda, is true. And yes, it's a bit ugly, and we have to take care to use non-local state to persist data between iterations. And all of this is just to satisfy some nostalgia and avoid a negation in the loop condition. But it's a glimpse into what decorators can really do. So just wait. Perl also has this gem, familiar to many C programmers. This is a do-while loop. It always executes the body of the loop at least once, and then it evaluates the loop condition before repeating. In certain cases, this can be helpful because it reduces duplication of setup code. Python has no native syntax for doing this, though. Exactly 22 years ago yesterday, PEP315 proposed new syntax to add a do-while loop to Python. For Python 2.5, PEP was deferred for years and finally rejected in 2013. I rediscovered it while writing this talk, and I think it's finally time we do justice for PEP315. So I'm announcing the public release of the do-while package on PyPI. It's available today, and you better believe I did it just for this bit. So let's see it in action. So this new package lets us finally write a do-while loop in Python, with the do decorator wrapping the body of the loop, followed by a call to the while function with an appropriate predicate. The predicate also prints the value here so we can confirm that it's being evaluated afterwards, not at the beginning. And so when we run this code, we can confirm that that's after the first iteration, thus ensuring the body is always run at least once, even if the predicate was always false. How does it work? Well, it's quite simple. The real package has a bit more to it, but it can be boiled down to this fragment. The do decorator function doesn't return anything, and it doesn't even run the loop. It merely creates and saves a wrapper, and then waits for the while function to be called. Only then does the wrapper execute using the provided predicate to control the loop. The release version also supports collections or other truthy objects as predicate, running the loop until those objects become falsy. This lets us clean up some uses of global or non-local and get by without a lambda for the predicate. I think this is about as nice of a do-while loop as we can get without modifying the Python runtime itself. And again, we can see the loop working as we expect with all of its post-evaluation glory. It's a great success. It's 2025, what'd y'all expect? All right, I get it. Let's climb back out of the rabbit hole. Decorators are passé. What we really want is control flow that we can use for good, not evil. Something like generators. Generators are a special type of function that can pause execution, yield arbitrary values, and then resume from where they left off. Writing any function with the yield keyword automatically turns it into a generator, and when reaching a yield statement, the runtime will pause execution of that function and pass that value back to whatever is consuming the generator. We can also use yield from, which will again pause our function, but now it will defer to any arbitrary iterable, yielding each of those values until it's exhausted, and only then resume our function afterwards. Unlike normal functions, though, when we call a generator function, it doesn't immediately start running. Instead, we get a generator object, and we need to do something with that object to make it start running and yield those values. Generator objects are themselves iterable, so the easiest thing to do is to loop over them. For each iteration of the loop, it runs the generator until it either yields a value or finishes. Once the generator yields a value, we can do anything we want in the body of the loop and with that value. Alternately, we can call next on the generator object to run it until it yields a value. And again, we're free to run arbitrary code until we're ready to resume the generator. But perhaps unexpectedly, we can also send data back in to a running generator, in between the yielded values that we receive from it. However, we need to stop treating generators like normal iterators or loops. We can do this by calling the send method on a generator object, and the value that we pass here will be sent into the generator. The generator function will run until it yields again, and that yielded value will be returned to us from the send method. On the function side, values sent into the generator are presented as the return value of a yield statement. Remember that when we first call a generator object, the function hasn't started executing, so there's no current yield statement to receive a value. That means the first time we call the send method, we must send none. Anything else will cause an exception. This is what actually starts execution of our generator function so that it can start yielding its first value. Now, if the generator raises an exception, that exception is also raised from the send method, and we can catch and handle that exception in our code. But like sending values back into a generator, we can also inject exceptions into the generator. The throw method will raise the given exception inside the generator function where it was left off, triggering the normal exception handling process. But do beware, if the generator doesn't catch the exception, it will be raised right back out from the throw method. Otherwise, we'll get the next yielded value in return. Lastly, when a generator function returns or finishes executing, it will raise a stop iteration exception just like any other iterable. We see that exception raised when we call send enough times to reach the return statement, and the value from our generator's return statement is available as a property on the exception object. Altogether, this gives us bidirectional communication between generators and the code wrapping them. This forms the foundation for concurrent, interleaved execution of two or more functions, commonly known as coroutines. Async I/O itself was built originally on top of generators with event loops that round-robin execution between multiple active coroutines. But that's a different rabbit hole for a different day, and I already gave that talk here back in 2019. So what else can we do with this? I'm sure many of you are familiar with or at least seen zip function before. Takes one or more iterables, produces tuples, combining the values from each of the steps of those iterables. We can build a version specifically for generators. Our version of zip can be relatively simple. We take any number of generators, call send on all of them in sequence, yield a tuple with the values generated from each of those generators. And yes, this is a generator that's pumping generators. But we will repeat this until one of the generators finishes and raises a stop iteration error. At that point, we can clean up any of the other unfinished generators by calling close on all of them, ensuring that each generator has the chance to run and clean the exit. We can use that with the toy function here and see that it generates tuples accordingly. It also stops correctly once the shortest generator is completed. None of this is really exciting or groundbreaking, though. So let's try to think outside the box. We know how to start generators. We can switch execution between multiple concurrent generators. How about a state machine? We could have each state be a separate generator function and use the yield statement to transition from one state to another. We can even build a bare-bones state machine in a single function. Given a starting state, we initialize the generator functions as needed, running the current state until it yields a new one, and then we repeat. We could also implement message passing between states, but we don't need that yet. This lets us write simple implementations for each state as individual generator functions separate from each other that yield the name of the function to transition to. And when we transition back to an active state, it'll continue running exactly where it left off. And when we start our state machine from state 1, we can see it transition to each new state, coming back around to the first one, resuming its execution, and then eventually the program ends once a function returns without yielding a new transition. Now let's do something fun with this. Introducing the Nbpy Python control flow text adventure. Text adventures were some of the earliest PC games ever made, and many are just a collection of rooms and actions combined into one giant state machine. Perfect for our toy project. We can build a simple text adventure, one room at a time, using our generator state machine with a few small changes. Each room, of course, is its own state. We can use a shared game object with data that will track across the rooms, and the logic within a room's function can interact with the user, change the game state, or yield a different function to transition the player from one room to another. So let's play our game. If you happen to have UV installed, you can play along from your own machine easily with this command and URL. That URL simply redirects to the latest version on the GitHub repo. So let's give this a try. All right, so you wake up in a bedroom, you feel tired, and the commands we have are either go east or sleep. What should we do? Sleep. All right. What a week. Wake up in a bedroom. Do you want to go east or do you want to sleep? Sleep. I hear sleep again. That sounds great. A little nap can't hurt. All right, we'll go east this time. You're in a hallway. We can go north, south, or west back to the bedroom. Sleep. Nope, sorry. Let's go. Do what? All right, let's go north. You're in the living room. North, south, east, or west? North. All right. You're in the kitchen. There is cake. Eat the cake. All right. You eat the cake. It has strawberry filling. All right. Let's go south. All right. You find yourself in a closet. It is dark. You pull the chain, but the bulb is burned out. Back in the living room, and now we'll do the last one. We go east. You walk out the front door, and it is a great day to be in Petaluma. All right. Thank you all. You were fantastic. For those wondering, the full game engine here for our text adventure weighs in at a hefty 28 lines of code, or about double that if we include the doc strings and white space. And the entire file with engine and generator functions for all the rooms is less than 200 lines of code in total. So, okay, I know we're running out of time, so where do we go from here? If there's one lesson here, it's that you should always write obvious code. Clear is better than clever. Everyone who has to read your code in the future, including yourself, will appreciate your obvious code. Often this takes more time than just writing code that works, but I urge you to take that time. Think about ways that you can use or abuse your language to make your code more obvious. Make the important code clear and concise and bulletproof. Just don't jump the shark. Maybe think twice before writing your loops with decorators. But above all else, have some compassion for your coworkers and your future self. As promised, the slides and example code, including the text adventure game, are all available on my GitHub repo. It also includes all of my past talks, so if you really do want to dive into Python grammar or syntax trees or the nerdy details of coroutines and async IO, there's something here for you. And thank you all for being here. I hope you enjoy the rest of North Bay Python.